box. Here we're looking at a 40-finger caliper in a 7-inch casing, and we can see the multi-finger caliper map, diagnostic track, and individual finger radius. Let's zoom in at certain interval, and we can clearly see that this is raw data before centralization. And as we see here, remember that the center indicates the low side of the cross-section. There are lower radius values, and this is a typical indication of eccentricity. For example, if we look at the cross-section, we can see, for example, in this particular interval, that there are lower values on the low side of the cross-section compared to the high side of the cross-section, okay? But if we look at certain intervals like this one here, we can see that this is exacerbated. And for example, we see a very large difference between the large radius compared to the low radius. And we also see a change in direction of the eccentricity up here, for example. Can you see? So this interval is basically showing a peak in the eccentricity and also a change in the eccentricity from pointing to one direction down here and 180 degrees opposite up there. Okay, so this is a clear indication of deformation. In this schematic, we see a multi-finger caliper tool initially moving through an undeformed casing section. As you can see, the multi-finger caliper is run in between two mechanical centralizers to minimize the eccentricity. Okay, so in an ideal situation, regardless of the position of the finger, this is the azimuth, the radius values measured by each of the fingers should be equal. In reality, especially when certain deviation exists, the tool will be slightly pushed towards one of the sides, the low side typically, and therefore some eccentricity will exist, as shown in this image. As the multi-finger caliper enters the deformed interval, the centralizers tend to remain constrained by the casing geometry, and the MFC tool is therefore pushed towards one of the sides of the pipe. And as we see here, as a consequence, some fingers will open more than other fingers, right? And this will cause the typical characteristic that at certain depth there are fingers with higher values, as shown here in green and yellow, and other fingers with lower values, as shown in blue. And this will cause a peak in the eccentricity. As the tool string exits the deformed interval, the MFC tool will be pushed towards the other side of the pipe, and the orientation or direction of the eccentricity will change. Now we can see that the fingers on this side will open less than these other fingers, okay? So in multi-finger caliper, deformation is typically characterized by these features, okay? So first, there is a sudden increase in the eccentricity and also a change in the eccentricity direction, right? So the eccentricity we will identify it by simultaneous high and low radius values at a particular depth. Let's go back to Emerald, and before analyzing the different deformation mechanisms, we are going to centralize the data. And for this case, we are going to use the default parameters. Once the data is centralized, the map doesn't show any characteristic sign of deformation. So why is that? Well, we must remember that deformation is just an excess of localized eccentricity with a change in direction. So when we apply the centralization algorithm, also the deformed intervals are corrected for eccentricity. And this removes any characteristic feature of the deformation in the map. The only remaining indication of deformation is the calculated eccentricity. Remember, this is the distance from the center of the multi-finger caliper to the center of the pipe. And this shows a number of peaks, right? And the value of the peaks are definitely much higher than the baseline eccentricity. Okay, so I'm going to move to a different interval where we can see a particular type of deformation mechanism. So at this depth, we have two areas with low radius values and two areas with high radius values, right? We can always extract the finger readings at this particular depth, and we can see two cycles of a sinusoid. If we look at the cross-section, we will clearly identify what we have here, and this is ovalization. Okay, so ovalization is the only deformation mechanism that survives decentralization, okay? If the raw data shows ovalization, after we centralize the data, the ovalization will remain there, okay? All the other deformation mechanisms will be masked or will disappear once we apply decentralization. So what we learned here is that multi-finger caliper data should never be centralized before looking at the raw measurements. Otherwise, we may miss the characteristic features of deformation, maybe causing later well entry problems, okay? Once we have centralized the data and we computed the eccentricity curve, we can right-click on the image and tick the Show Centralization. So this will show the data before centralization, but will keep the eccentricity curve. And this is the ideal way to identify deformation mechanisms. Okay, so let's go down. And for example, what we see here at this particular depth is 3 peaks in the eccentricity and 3 changes in eccentricity direction. Okay, so this is telling us that the direction is changing twice, okay? And this is typical of a bend or like an elbow, right? We can also see this in the 3D display. And using the navigator, I'm going to select the interval for display, which is this one. Okay, and here we can start to see the characteristics of this bend or elbow, as I call it, okay? So as mentioned, there is one change in direction and a subsequent change here. Okay, so we have free 3D rotation. We can take measurements of the length between 2 points of interest. The other interval of interest is up here, and the deformation type is quite different. If you remember the bend, there were just 2 changes in eccentricity direction. Here we can see many peaks, 1, 2, 3, 4, 5, 6 peaks actually. And can you see that the eccentricity direction is not changing suddenly, like 180 degrees, like a planar deformation, but here the eccentricity is changing gradually and like clockwise, right? Like a corkscrew. So this is what we call helical buckling. So if we go back again to the 3D display, we're going to look for this helical buckling interval, and it's here. So we just select the interval for display. And there we go. We can see that the characteristics of this deformed interval are quite different compared to the bend. Again, the deformation is more progressive and it's not like a planar change. It doesn't change 180 degrees, but it's slowly rotating clockwise or anti-clockwise. Finally, here we can see a shear deformation where there are essentially 2 peaks in the eccentricity and a single change in eccentricity direction. Okay, so this represents a single deformed plane, and this is how shear deformation looks like in 3D display. Okay, so we can display again the centralized data. And here we are. Remember, the only thing that survives centralization is the ovalization, right? And here we have a few intervals with ovalization. So what about all the statistics that we have calculated? For example, if we bring the metal loss or the penetration, are these valid? Okay, these are calculated with the centralized data, and this will be valid as long as the fingers are still in contact with the pipe wall. And this is not always the case. Remember that sometimes due to a very large eccentricity, if the finger length is not long enough, some fingers may not touch one part of the pipe, okay? So as we zoom in now, we can see that even though this is the form interval as seen in the eccentricity, the multi-finger caliper still detects the perforations in this particular case. Okay, I hope this video was useful and see you next time.